Good evening everyone, I am Shivani Dhok and I welcome you all for the week 12 tutorial for the course of simulation of communication systems using MATLAB. So like every time, this week's tutorial will also be divided in two parts. The first part will be recap of week 12 content and followed by the questions which are related to week 12 content. So let's start with the recap of week 12 content. So week 12 content first lecture was simple DPSK and it just finished DPSK simulation. After that, a very brief week it was, like very less content was covered, but it was an important content and which looked at an important concept of wireless communication. So what do you mean by wireless communication is your transmitter and receiver are not co-located and they are not connected through any wired medium and they want to communicate with each other, and the medium in which they will be communicate will be unwired, so maybe free space or something like that. And in this wireless communication we saw that we get the receiver or the receiver sees multiple attenuated and delayed copies of the transmitted signal. So what happens is, suppose I have a transmitter here and let's say I have a receiver here, and both of them are separated and both of them are trying to communicate wirelessly. So in our atmosphere, in our environment, so there will be multiple objects. So there might be some car, or there might be some building or some tree. Multiple things might be present in the environment. So what happens is, this wants this particular kind of communication. So basically this transmitter wants to communicate to this receiver, and if this particular link, like direct link between your transmitter and receiver is available, then this kind of link is known as line of sight. And along with line of sight, there might be multiple copies of the same signal that shall come from the refractions and diffractions from these objects. Multiple reflections from same object can be there like this. So all of these blue things or blue colored parts, these are diffracted or refracted components of your signal, of the same signal that your transmitter is transmitting, and this is known as non-line of sight. Now this receiver might move. Along with that, this environment might change. There will be wind, so the position of the leaves will change. Then something might happen inside this building, so that parts will also change. This vehicle will move. It might happen that after a particular time, this vehicle is not there. So this environment around us will be changing randomly. And therefore, the number of reflected copies, the delays, and the amplitude, whatever you will be receiving, will be again random. So there will be some this kind of randomness in terms of delay and attenuation also. That leads to fading. So this fading here, this fading is basically change in signal amplitude, and phase due to reflections. And there are different ways to model the fading, and one such way is Rayleigh fading. So for Rayleigh fading, what happens is, for Rayleigh fading, you have large number of reflected signals at your receiver, and in such situation you can model your channel as Cn 0 comma sigma square, where this particular symbol here means it is circularly symmetric complex Gaussian. Okay, and this particular leads to Rayleigh fading. So what it means, the channel is Rayleigh faded, is the envelope is distributed as a Rayleigh random variable. Okay, then we have CSI availability. So this CSI, we had seen different types of modulation, demodulation techniques earlier, decoding techniques. One was coherent detection. So for coherent detection, you need CSI at the receiver. So for coherent detection, we need CSI. And what do you mean by CSI? CSI stands for channel state information. And there is a whole class of approaches through which we can do, and so these techniques are known as channel estimation techniques. These enable us to find the channel state information, or in rather find, will can estimate, not find. So this is not going to be covered in this particular course. Very basics of wireless communication will be covered. So this page. After that, we looked at multi-tap channels. So this multi-tap channel, what happens is you have multiple reflections. So these multiple reflections you can characterize using multi-tap channel. So this multi-tap channel you can write as y of t as summation k. So k is the tap index, hk, t tau k, s of t minus tau k. So here hk is the channel coefficient, tau k is your delay, and here this thing here is your delayed version of your signal. Delayed version of transmitted signal. Okay. Then there are different types of channels. One will be time selective. So what it means is the channel changes very frequently with time. Then another thing is frequency selective. So the channel will change with frequency too. The frequency response will not be constant for all the frequencies. And doubly selective means it will change along the time axis and also along the frequency axis. And this channel can be denoted by symbol NK. And the way your channel varies or how it is affected in time and frequency. So four different metrics are used. One is delay spread, another is coherence bandwidth, then we have coherence time, and then we have Doppler spread. So what do you mean by delay spread? So it is the difference between your maximum delay and the minimum delay. So this is the difference between the maximum delay and minimum delay. Then you have coherence bandwidth. So this particular thing, so this is bandwidth for which channel remains constant, or channel is approximately constant. Then you have coherence time. So this is the analogy, same thing like coherence bandwidth, bandwidth in which the channel remains approximately constant. Same thing is for coherence time. So this is time in which channel is approximately constant. And then we have what is known as Doppler spread. So this is the difference between minimum and maximum Doppler frequency. And from where does this Doppler frequency occur? So this Doppler spread, this occurs due to mobility, or let's say movement of your transmitter, receiver, or any component in the environment. So whenever this Doppler spread basically characterizes the effect of mobility in your communication channel. So this was all that was covered in this particular week. If you have any questions, then let me know. Otherwise, I'll move on and cover the questions that I have planned to take. Okay, if there are no further questions, then let me move on to the first question that I have planned to cover today. So this question set is also a mix of 2-3 previous years questions and few other questions. So the questions that I'm trying to cover today will give you a basic information about fading, and we'll try to simulate whatever we derive. However, not too much detailed things might be asked, but again, Another thing that I would like to mention before starting the questions is I will be taking a summary session on 28th of October, 20 October, that is Sunday, and that will be 11 a.m. And if you have any queries regarding that any queries which you want me to solve in that session, then I request you to post your queries by 15th of October in the portal. In the question and answer portal, I'll be happy to solve them in your summary session. Any question, any assignment doubts, except I think week 12. So till the time your week 12, suppose your week 12 assignment deadline is already done, you can post questions related to that also. Okay, with that, if you have no questions, then let me move on to the next question. So here it is given, so this is last year's question. So it says that H is Cn 0 comma sigma square, represents a complex Gaussian random variable with dash mean and variance and dash variance, and write its PDF. So this, when we write this H as Cn 0 comma sigma square, this actually means is H is circularly symmetric. This is in general, unless mentioned otherwise. Circularly symmetric complex Gaussian random variable. What it means is, same way as your Gaussian random variable, the first entry means it is a mean and the second entry means it is the variance. So if you compare that, then this particular thing here is your mean and the sigma square here is your variance. Okay, so this is a zero mean and sigma square variance complex Gaussian random variable. Now what we need to do is we need to write its PDF. Now this is a complex Gaussian random variable, and generally we haven't seen how to handle these complex Gaussian random variables. So assuming it is a circularly symmetric complex Gaussian random variable, what we can do is we can write this H as HR plus JHI, where this HR is real part of H and this HI is imaginary part of H. Okay, and for a circular symmetric complex Gaussian random variables, this HR and HI are IID Gaussian random variables with zero mean and variance sigma square by 2. So what we have is this HR is distributed as Gaussian with mean 0 and variance sigma square by 2, and in similar way your HI is distributed as Gaussian 0 comma sigma square by 2, and these two are basically your IID. So these two are IID. Okay. Another thing is we want to write its PDF, right? So we have this H as HR plus J times HI. So this is a complex Gaussian random variable. We can treat this complex Gaussian random variable like a random vector. So we can treat this as, or rather treat, we can visualize this as a Gaussian vector, or yeah, a Gaussian random vector. which is your HR and HI. And PDF of H is basically equal to your joint PDF of HR and HI. Okay, now since HR and HI are independent, here the joint PDF will be PDF of HR into PDF of HI. So therefore, your FH of H is nothing but your FHI of HI into FHR of HR. Okay. This is because since HR and HI are independent. Okay, so therefore f of h equal to what is PDF of your HI? So it is a Gaussian random variable. So 1 upon under root of 2 pi into its variance. Variance is sigma square by 2 into e power minus hi square by 2 into its variance. And similarly, what is the PDF of your f of HR? HR, that will be equal to 1 over, again same thing, 2 pi sigma square by 2 into e power minus HR square by 2 into sigma square by 2. So if we simplify this, if I combine these two things, so that will be equal to 1 upon pi sigma square into e power minus HR square plus HI square upon sigma square. Now what is your HR, what is this quantity here in the exponent? This thing is basically absolute square of your HR plus J times HI square, which is simply HR square, which is simply your magnitude of H square. So therefore your FH of H comes out to be equal to 1 upon pi sigma square into e power minus mod h square by sigma square. And this is exactly the PDF which we have been using till now when we considered complex Gaussian noise. Is it clear? Any questions? Okay, if there are no questions, then let me move on to the next question. Okay, so this is not sort of a question but an concept kind of thing. So here it is asked is how do we come up with Rayleigh fading channel model for wireless communication channels? Okay. So what happens is we have seen that we receive multiple copies or we have multiple reflections of the channel. So we can write a communication channel. So we can, so let H be the channel gain or channel coefficient between a transmitter and a receiver. So this h we can write as, h is a complex quantity, so we can write it as summation I equal to 1 to n ai into e power j or minus j 2 pi fc tau I. So what do we mean by n here? So this n here, this n indicates number of reflected components or reflected signals or reflected copies of received signal or number of paths. Then you have this AI. This AI is amplitude, attenuation, or amplification factor of ith path. And this tau I is basically delay introduced by ith path. Okay, so therefore what we have is, we have this h as summation I equal to 1 to n ai e power minus j 2 pi fc tau I, where your fc is the carrier frequency. So this you can write as summation I equal to 1 to n ai, and this e power minus j 2 pi fc tau I you can write as cos of 2 pi fc tau I minus j times sine of 2 pi fc. Okay. That you can separate it out, summation I equal to 1 to n ai cos 2 pi fc tau I minus j times summation I equal to 1 to n ai sine 2 pi fc tau I. Okay, so this is what we are having right now. Now what we can do is, we can write this as hr, this part as hr, and this part along with the minus sign as hi, or we write it in this way, j times hi. So your hr is summation I equal to 1 to n ai cos 2 pi fc tau I, and your hi is minus summation I equal to 1 to n ai sine 2 pi fc tau I. Okay, so this is what we have reached to. Yeah, HR and HI, these are the things that we have. So now if n is very large, then before doing that, what I'll do is let 2 pi fc tau I defined as phi I. So then your hi is summation I equal to 1 to n ai cos phi I, just to avoid writing the 2 pi fc tau I multiple times. And your hi will be equal to minus summation I equal to 1 to capital N ai sin phi I. Okay. Then for large n, okay, before that, there are some assumptions that we take for doing this. We say that this ai and aj are independent for all I not equal to j. Then we have phi I and phi j independent for all I not equal to j, and phi I is distributed as uniformly in 0 to 2 pi or minus pi to pi. Anything is fine. And your ai and phi j are independent for all ij. Okay. So now if this is the case, then your ai cos phi I are independent of your aj cos phi j. Similarly, your ai sin phi I are independent of your ai sin phi j. In that situation, these are both are summations of your independent random variables. So therefore for large n using central limit theorem, we have HR distributed as Gaussian with mean of HR and variance of HR, and HI distributed as again Gaussian with mean of HI and variance of HI. So let's figure out what is the mean of HR and mean of HI. So expectation of your HR is equal to summation I equal to 1 to n expectation of AI cos phi I. Since AI and phi I are independent, we can write it as summation equal to 1 to capital N expectation of AI into expectation of cos of phi I. Why is it so? Since AI and phi I are independent. And now let's say we don't know what is expectation of AI. Let's first figure out what this thing is. So this is equal to 1 over 2 pi integral 0 to 2 pi. Why? Because your phi I is a uniform distributed random variable in 0 to 2 pi. So the PDF of that thing is basically 1 over 2 pi into cos of phi I d phi I. This comes out to be equal to 1 over 2 pi into sine of phi I from 0 to 2 pi. So you're integrating sine over a period. And when you integrate any sinusoid over a period, it gives you 0. Or any integer multiple of period, it gives you 0. So therefore, expectation of HR comes out to be equal to 0. similarly, let's find out what is expectation. Okay, before that, let's find out what is variance of HR. So your variance of HR is summation I equal to 1 to n into variance of AI cos phi I. And why is it so? This is because your AI cos phi I is independent of your AI sin phi AI, sorry, AJ cos phi j. So your variances also sum up. This is equal to summation I equal to 1 to n variance of AI. Okay, so this is equal to expectation of AI square into cos phi I cos square phi I. This is equal to summation I equal to 1 to n. Again, we have expectation of AI square into expectation of cos square phi I. This is because again they are independent. AI and cos phi I equal to 1 to n. Expectation of AI square into integral 0 to 2 pi 1 over 2 pi cos square phi I, that I can write as 1 plus cos of 2 phi I by 2 d phi I. So now this particular integral here, I can write as 1 over 4 pi integral 0 to 2 pi 1 d phi I plus 1 over 4 pi integral 0 to 2 pi cos of 2 phi I d phi I. This particular thing is 0 and this particular thing is equal to 1 by 2. Okay, so what we get as your variance is, so therefore variance of HR comes out to be equal to summation or half of summation I equal to 1 to n expectation of AI square. Okay. Now in similar way, we can figure out what is your expectation of HI. So that is equal to summation I equal to 1 to n expectation of AI sin phi I. Again, this thing is equal to your expectation of AI into expectation of sin phi I. And since again you are integrating your sine over a period, this comes out to be equal to 0, similar to your cos. So therefore this expectation is also equal to 0. Similarly, you can find out your variance of HI. So this comes out to be equal to summation I equal to 1 to n expectation of AI square into sine square phi I. This comes out to be equal to summation I equal to 1 to n expectation of AI square into expectation of sine square phi I. This is equal to 1 over 2 pi integral 0 to 2 pi. Again sine phi I can write as 1 over cos of 2 phi I by 2 d phi I. We have seen that integral of this particular quantity is equal to 0. So again this particular thing reduces to half. So therefore variance of HI comes out to be equal to half of summation I equal to 1 to n expectation of AI square. So what we have till now is HR is Gaussian with 0 mean and variance half of I equal to 1 to n expectation of AI square, and HI is again Gaussian with 0 mean half of summation I equal to 1 to n expectation of AI square. Now let us figure out what is your covariance of HR and HI. So expectation of HR HI is equal to expectation of summation I equal to 1 to n summation m equal to 1 to n ai am cos phi I cos of phi m. This comes out to be equal to summation I equal to 1 to n summation m equal to 1 to n expectation of ai am to expectation of cos of phi I cos of phi m. So this particular thing here, that is expectation of cos of phi I cos of phi m, is equal to expectation of and yeah, this is for sorry, second, can show that I won't spend too much time in this now. We are already running in time. You can show that these are independent. So these two are basically IID. So your H equal to HR plus J times HI. Since these are IID and these two are jointly Gaussian, is circularly symmetric, complex Gaussian with mean added, that is zero mean, and variance added. So variance will be summation I equal to 1 to n expectation of AI square. So this is the variance. So this is yes, and we will see in the subsequent questions that magnitude of this, which is under root of HR square plus HI square, this thing is Rayleigh distributed. So the main takeaway from this particular question is when you have a large number of reflected components and there is a non-line of sight path, then in such a situation you can model your channel as a Rayleigh faded. Any questions? These things I'm taking up because these are good to know when you study wireless communication, nothing else. So I was not able to take up too many questions which were there in your assignment because they were all repeated from last year. So it's better to dig into more concepts rather than looking at those assignment questions, which I will be happy to solve in your summary session. Okay, so let's start with question number 3 now. So suppose z equal to x plus jy and x and y are IID zero mean Gaussian random variables with variance sigma square. Find the distribution of magnitude of z. So what we have is, so what I'll do is I'll write this magnitude of z as a. So let's say this a is your magnitude of z, and what is given to us is your z is x plus jy. Okay. So this is a complex random or a complex number. This any complex number we can either write it in a Cartesian form or a complex form. So z I can equivalently write as magnitude of z into e power j, angle of z. So this is magnitude of z, let's is a, and your e power j angle of z, let's say, is theta. Okay, so what happens now is, in Cartesian coordinates, your x and y are two random variables, and in your polar coordinates or polar representation, your a and your theta both are random variables. So we can write this as, what we need to find out is your PDF of your a. So we have this, equivalently we have this x and y random variables, and in order to figure out what is the PDF of your a, we'll take up this a and theta as to another random variables. Now what happens in general, so we have this is given to us. How it is given to us? Because we know that x and y are IID, 0 means sigma square variance random variables, and in similar way we have this a theta, and we need to find f a theta of a comma theta. Okay, this we don't know. So this thing that we need to do is known as transformation of random variable. And for this particular thing, we can have, you can look at the Jacobian based formula for transformation of random variables. So using the Jacobian formula of, or for transformation of random variables, f of a theta, a comma theta, we can write as determinant, or okay, magnitude of determinant of j into fxy of, so this is, you know that this a is equal to your x cos theta, or not like that, your x a cos theta and a sin theta. So this thing will be equal to your a cos theta, that x evaluated at a cos theta, comma y evaluated at a sin theta. Okay, so we know, okay, we know that x is Gaussian 0 sigma square, and y is again Gaussian with 0 mean and variance sigma square, and these two are IID. So therefore your f of xy, x comma y, will be equal to fx of x into fy of y. Okay, so what is your fx of x? This is equal to 1 over 2 pi sigma square e power minus x square by 2 sigma square multiplied by 1 over under root of 2 pi sigma square into e power minus y square by 2 sigma square. So this I can combine as 1 over 2 pi sigma square into e power minus x square plus y square by 2 sigma square. Okay, so this is the PDF. And another thing that we need to figure out is what is your Jacobian matrix. So this J we can write it as del x by del theta, del y by del theta. Let's do it for A first, del A, then del x by del theta, again del y by del theta, and okay. Now what is your x? You can write it as rho by rho A of A cos theta, then differentiating with respect to A for A sin theta, then same thing with respect to theta now, A cos theta, and partially differentiating with respect to theta, A sin theta. Okay, this is a matrix, not a determinant. Okay, yeah. So this is what we have now. And now we can write this as cos theta, sin theta. Then differentiation of cos theta is minus sin theta. So I have minus a cos, sorry, minus a sin theta. And this is a cos theta, which implies if I take determinant of j, that will be equal to a cos square theta plus a sin square theta. That comes out to be equal to a. So therefore, let us substitute back these two things in this equation now. So let me number this equation. This is 1, this is your 2, and this is 3. So therefore, from, or rather substituting 2 and 3 in 1, we get f of a theta, a comma theta, as your determinant of your Jacobian comes out to be equal to a multiplied by your joint PDF, which is 1 over 2 pi sigma square e power minus, or rather, right, let me write it as exponential of what is your x square. X square will be a square cos square theta plus a square sin square theta divided by 2 sigma square. So that is equal to a upon 2 pi sigma square e power minus a square by 2 sigma square. So this is a joint PDF of your angle and your magnitude. But we wanted the PDF of only your A. So therefore, the marginal PDF will be equal to integral 0 to 2 pi, that is integrating over the entire range of your theta variables in angle. So therefore integrating it over the range of angle, that is 0 to 2 pi, a upon 2 pi sigma square e power minus a square by 2 sigma square dA, d theta. So now everything is constant and I can take it outside. So this will be equal to a upon 2 pi sigma square integral from this exponent can also come outside, e power minus a square by 2 sigma square integral 0 to 2 pi d theta. So this comes out to be equal to a upon 2 pi sigma square e power minus a square by 2 sigma square into 2 pi. So this is therefore f of a little a comes out to be equal to a by sigma square e power minus a square by 2 sigma square, and this is for a greater than or equal to 0. Is it clear? Any questions till this point? So this is the PDF of your uh, envelope or magnitude of the random variable, and this is basically PDF of a Rayleigh distributed random variable or a Rayleigh random variable. Any questions here? Okay, if there are no questions, then let me move on to the next question. So next question says, in the previous question, find the distribution of angle of z. So we had defined this angle of z as theta. Okay, so now we had this joint PDF of f of a comma theta, and now we had find out what is the PDF of your a. Now in similar way, we need to figure out what is the value of your theta. So from previous question, we have the joint PDF of theta and a. So we have this f of a theta, a comma theta as a over 2 pi sigma square e power minus a square by 2 sigma square. I think 2 was not there here, sorry. A sigma square e power minus, sorry. No, it was there. 2 pi sigma square. Yeah. Okay. So therefore, marginalizing with respect to a, we get f of theta little theta as integral 0 to infinity a upon 2 pi sigma square. A is a magnitude, so it is a positive quantity, or rather it is a non-negative quantity. It can take a values from 0 to infinity. E power minus a square by 2 sigma square dA. Okay. Now let us take out the constant terms outside. Okay. Just a minute. Yeah. So let us take out the constants outside. So what are your constants? Those are 1 over 2 pi. Let us keep the constant sigma square inside only. A over sigma square into e power minus a square by 2 sigma square dA. Now what we will do is a quick substitution. So we will substitute e power minus a square by 2 sigma square as t. So therefore we have minus a by sigma square into e power minus a square by 2 sigma square dA equal to dt. Let us substitute this back. So therefore your f of theta little theta comes out to be equal to 1 over 2 pi integral. So now your limits become, so it is first 0. So 1 to 0 and minus dt. So this now becomes 1 over 2 pi integral 0 to 1 dt, which is equal to 1 over 2 pi. And this theta is from 0 to 2 pi. So therefore this theta is uniformly distributed from 0 to 2 pi. Is it clear? Any questions till this point? Okay. Okay, if there are no further questions, let me move on to the next question then. So this question says that in question 3, find the distribution of a square. So what was your a? A was your amplitude, and what we know about a, your f of a is basically equal to, so your f of a comes out to be equal to a square, sorry, a by sigma square into e power minus a square by 2 sigma square. Okay, so this is what we have, and this is for a greater than or equal to 0. And let's say your b is your a square, and we want fb of b. Okay, we want this. So for that, what we'll do is we'll write it as fb of b is basically your derivative of your CDF, and your CDF is basically probability that your b is less than or equal to little b. That is probability that your b, so b here, a square is less than or equal to b. Why? Your b is equal to a square. We have defined that. So therefore we can write it as probability that your a is less than or equal to under root b. Since it is from 0 to infinity, this is okay. So this comes out to be equal to your CDF of a evaluated at root b. Okay. So now what we need to find out is your fb of b, which is equal to derivative of fa of, sorry, fb of b, which we can write as derivative of fa root b from this particular derived equation here. So now if we and we, another thing that we know is derivative of this this thing fa of a, or rather we can write here, we can write fa of a as dda of fa of a. So we know that. So now if we do this, then this will be equal to derivative with respect to, so we'll have this multiplied by 1 over 2 times under root b. Okay, so what is your, so we have fb of b, this is equal to fa of a. What is your fa? This is a in upon sigma square, so your a is basically your root b multiplied by 1 over 2 root b into e power minus, what, it was a square, so now it will be b by 2 sigma square. So this b gets cancelled, so what we get is 2 sigma square e power minus b by 2 sigma square for b greater than or equal to 0. And this particular random variable is known as exponential random variable. Okay, any questions till this point? Okay, yeah. So now we can simulate. Now let's move on to the next section or next question. So it says that, so what I'll do is both question 6 and question 7 are simulation based questions. So these these simulation questions I will solve at the same time together, and so what is asked in those simulation questions is, first we need to simulate z, then we need to simulate a, which is your magnitude of z, and then we need to simulate theta, which is your magnitude of angle of z. And after that, what we need to do is we need to look at this magnitude of z square, that is your a square, which is b, and match it with the derived PDF or CDF. So let's do it for your PDFs. Okay, so we'll also do it. Okay, so let's do it now. So for that, what I'll do, I'll share my laptop screen. Okay, I hope my screen is visible. Okay. Okay, so let me just start with this. I'll write what the question is. This is not week 10, this is week 12. Okay, yeah. So this is question. So this is basically your question 6 and question 7. So question 6 is simulate z equal to x plus jy, where x and y are IID Gaussian with zero mean and variance sigma square. This is first thing that you need to do. Then second thing that you need to do is simulate a equal to magnitude of z, and third thing you need to do is simulate do this. PDF of PDF of theta equal to angle of Z. And then we have question 7. Simulate b equal to a square, and for both question 6 and question 7, match the PDF or the analytical PDF of A, theta and B. Okay, so let's start. So for first, what we need to do is we need to generate Z, and for generating this Z, what we need is basically we need to generate your X and Y Gaussian random variables, and for that we need two things. One is number of realizations or the number of times we need to generate that random variable, and second thing we need to know is what is the variance sigma square. So let us first define n as 1e plus 4 for now. Then let us define your sigma square. Let's say it is unity for now. We'll change it. We'll see how things vary. Okay, fine. So now let us first generate what your Z. So get Z equal to x plus jy. So for that we need x. So your x is basically your Gaussian random variable. And how many do we need? We need n comma 1, and this is a standard Gaussian random variable, so therefore we need to multiply it by its variance, standard deviation, not variance. So this will get multiplied by your square root of your sigma square. Okay, similarly you have y as square root of 2. No, sorry. Yeah, this is only what we want. Same thing, because x and y are IID, and then your z will be equal to x plus 1i into y. Okay, so let us run this first. So when we run this, we get our z. Now what we can do is, let us just see how the PDF looks. Histogram of x. So this is the PDF. Another way to generate your PDF is a function known as Ks density. So you can take Ks density of x, that will give you PDF. And now if I hold on and plot Ks density of y and see the figure, so if you observe, they will overlap. Just a minute, what I'll do is, okay, so this is the PDF. If I generate it for larger number, let's say equal to 6, and if I run it, and if I again plot case density like this, so if you observe, both of them are overlapping, so you won't be able to see it right now. So if I delete this, you can see the another curve. So there are basically two curves. There are two curves. If I remove this orange curve, you can find the other curve also. So that will give me, so it says that both are IID, both are identically distributed random variables. Okay, and this z is x plus jy. So now from this z, what we can get is, we can get your magnitude of z. So your get a as magnitude of z and theta as angle of z. Okay. So now you have your x, or let's say z, sorry, a as absolute value of your z and your theta as angle of z. Okay. Now what we can do is can plot sorry figure ks density of a, and in similar way we can plot k figure ks density of theta. Okay, and now if I run it, this is something like a uniform random variable that is showing up, and this is some random variable which we don't know, and but we have the values of PDFs for both of these cases. So now what we can do is we will basically plot the analytical equations also. So let's say this A is some linspace of 0 to, let's say, max of whatever value A has, comma, let's say some 1,000 samples, and your FA of A, which is your PDF of your analytical equation of your PDF. So this was basically sigma square, sorry, A divided by sigma square multiplied by e power minus a square by 2 into sigma square. Okay, so this is your PDF that we have derived. So now let us first plot, or let's keep it like this here. Then what we can do is we can do hold on, and we can do this. We have this hold on. Then we can do plot a comma fa. Okay, and let's put markers for this. Okay, let it be like this only. And similarly, we have this theta as minus pi to pi. Let's take it from linspace minus pi to pi, and f theta is 1 by 2 into pi. Okay, and again what we can do is we can plot sorry can do hold on and plot theta comma fth. Okay, and to understand which plot is what we'll do is we'll add legends. First one is simulation, second one is analytical, then here again same thing, what we'll also do grid on, then we can just hold off, same thing we can copy paste here, and again what we will do is we'll just add a title also, PDF of A, and here we will add title PDF of theta. if I run this, what is happening? So if you see this, I don't know, where is this? Something is wrong in this figure. Oh, sorry. So this should be like once length of theta comma 1. Now it should be fine. Yeah. So now if you see this is very close to a uniform distribution. And if you observe this particular PDF, it overlaps. So the analytical equation, whatever we had derived, was exactly is correct. So this is how generally the simulations help to solve or to analyze whether the derived analytical expressions of any problem in communication system is correct or not. So now what we have done, we have done simulation of Z. We've derived, we matched the PDF of A, we matched the PDF of your angle. Now let's move on to the seventh question. The seventh question is simulate the PDF of B equal to A square. So we have our A. So now get B equal to A square. We have our A. So simply what we need to do is we need to define B as A square. We have our A here, which is absolute value of Z, and this is your B equal to A square. And now what we can do is same thing we can do, figure Ks density of B, and what we can another thing that we can do is we had derived its analytical PDF. So let's say this FB is the analytical PDF. This was 1 by 2 into sigma square multiplied by e power minus some b divided by 2 into sigma square. And what is your b? B should be some vector in space, again from 0 to, let's say, max of whatever value b takes, comma, let's say some 1000 samples. Okay, so now we can plot that. So we can do, hold on, plot b comma fb. Same things we can add legend, simulation analytical, and now this is PDF of your B. And okay, now if I run this, there is some error, I think. Oh, sorry. This little space. So now if you see, this is your simulation, this is your analytical. So basically you can ignore anything that is happening before 0, but now after 0, whatever line you can see, it's exactly matching. Okay, so this is also correct PDF. So this is how generally you simulate your PDFs, and generally this is the starting point of any communication system simulation when you for wireless communication. If you have any questions in this MATLAB code, then please let me know. Otherwise, I'll move on to the next question. I'll upload this code file in the Google Drive. Okay, if there are no questions, then let me move on to the next question. Okay, so just let me write it down here. Same thing for question number 7. So if that's done, let me move on to the next question then. So this is the 8th question. So generally, your channel in time domain or in continuous time domain is represented something like this. So this is your HT, that is your channel. So your HT is A into delta T minus tau, and then this, just a minute. Yeah, okay. Okay. So this we have here. So this HT is A into delta T minus tau, where this delta is your unit impulse. This A is amplitude change, and this tau is delay. So since it has only one amplitude change and one delay, such kind of channel is known as single tap channel. So this is all in time domain. Okay. So now what we need to do is we need to comment on its frequency response. Okay. So we need to find out what is its magnitude of Z. We want magnitude of H of F, where where HT Fourier transform is your H of F. Okay. So let us first find out what your H of F is. So H of F is basically Fourier transform of your HT, that is A into delta T minus tau. Your A is constant that I can take outside, and then it is simply integral minus infinity to infinity delta T minus tau into e power minus j 2 pi ft dt. This is equal to A times, we can use the shifting property. So that will give me A into e power minus j 2 pi f tau multiplied by integral minus infinity to infinity into of the impulse, and integral of any impulse over the entire time range is equal to 1. So this is what we get. Okay. So now if I look at magnitude of HF, That comes out to be equal to magnitude of A into e power minus j 2 pi f tau. And magnitude of this e power minus j 2 pi f tau is 1. So this is equal to magnitude of A. Now if I plot it with respect to frequency domain, so frequency, so this is your f, since this is your 0, and this comes out to be equal to your magnitude of A, or rather A, no, magnitude of A. Yeah. Okay, so this is what you get. So what you observe here is, so this thing here is basically magnitude of h of f. So you observe from the figure that we observe that magnitude of h of f is not a function of f, it is constant for all f. Okay, or in other words, what we can say is magnitude of h of f is affected by the same way for all frequencies. In the same way for all f, it is flat for all f, and such a channel in which there is no dependence or no dependence on frequency is known as a frequency flat channel. So such a single tap channel, or this particular channel, is referred to as frequency flat channel. Is it clear? Any questions? Okay, if there are no questions, then let me move on to the ninth question. So now I have another channel which is given by ht as a0 delta t minus 5 plus a1 delta t minus 6 plus a2 delta t minus 2. What we need to do is we need to find the delay spread. We had seen in the lecture, in the initial revision, we want to find delay spread. And what is this? This is maximum delay minus minimum delay. Okay, so this channel has three delay components. So we have three different delays which constitute three different taps. So such a channel is known as multi-tap channel. Okay, so this is a multi-tap channel. And how can you visualize it? So if I plot it with respect to time, so let's say this is your time axis, this is your h of t, and then we have, let me mark also, this is 0, this is 1, 2, 3, 4, 5, 6. Okay, so the first tap is at t equal to 5. So here it is, and its amplitude is a0. Then second tap is at t equal to 6. let's say here, and it is having an amplitude of A1, and the last tap is at equal to 2, which is something like this, and this has an amplitude of A2. Okay, so there are only 3 taps, that is, one is located here, another is here, and another is here. So what we know is this particular thing is the first delay, and this one is the last delay, and this duration from 2 to 6, this is your delay spread. So delay spread by its name means how much is the delay taps, how much are the delay taps spread in your along your time axis. So therefore your delay spread is your maximum delay is 6 minus 2, that is equal to 4 with some units, let's say seconds, or with some units, some time unit. Any questions? Is it clear? Okay, if there are no questions, then let me move on to the last question for today. Okay, so the last question says, what is the frequency response of the channel in question 9? How is it different from that in question 8? So this is the channel tab that we have in our question 9. So what we had h of t as a naught delta t minus 5 plus a1 delta t minus 6 plus a2 delta t minus 2. Now we need to figure out what is its what is the magnitude of its Fourier transform. So for that, let us first find out what is the h of f. So that will be equal to a naught into e power minus j 2 by 5 tau, sorry not tau, f, plus a1 into e power minus j 2 pi 6f plus a2 into e power minus j 2 pi 2f. So what we get is a naught into e power minus j 10 pi f plus a1 into e power minus j 12 pi f plus a2 into e power minus j 4 pi f. And therefore magnitude of h of f will be equal to magnitude of a naught into e power minus j 2 pi f plus a1 into e power magnitude of j 2 pi f plus a2 into e power magnitude of j 4 pi f. We are not able to understand what exactly this thing or how it looks. So for that, let us again take help of MATLAB. So let me simulate it, and I'll paste the figure in the in your uh, notes also. Okay, so let me go to MATLAB now. Yeah. So this is CLC, clear, close all. Then this is your question 10. We are visualizing the frequency response of h of t of h of t equal to a0 delta t minus 5 plus a1 delta t minus 6 plus a2 delta t minus 2. And next thing that we'll do is we will compare it with the frequency response of h2 of t. Say this is h1 of t, h2 of t equal to a delta, let's say t minus some tau. Okay. So let us first get h1 of f. So that will be equal to, so let's say h1. For that, let's first define f as length space of minus 10 to 10 with 1000 values. Then I have h1 of f as a1, sorry, a0 into e power minus j just a minute, e power minus j 10 pi f plus a1 into e power minus j 6 pi f plus a2 into e power minus j into 4 pi f. Okay. But first we need to define what your a1, a2, a0, a1, a2 are. So a0, let's say 1. Let us keep it all 1. a1 equal to 1 and a2 equal to 1. Okay. And similarly, so what we can do is we will plot f comma absolute value of h1. Let me run this. So this is your question 10 of week 12. Okay, so this is something that we are getting. So let me just reduce the time scale. Let me do it for minus 2 to 2. This is something that I am getting here, and let's try to make it a little bit weird. Okay, so something like this we are getting, and let me make this as 10, let's say. Okay, let's make it smaller. Let's keep it 1 only. So if I change the magnitudes or amplitudes, things change. Okay. Okay. So now let us get your h2 or absolute value of your h2 of f. So for that, let's say my a1 is a is 2. So and therefore your h2 will be once length of f and this will get multiplied by a. So now let us plot h2. So for that I'll use hold on. Plot f comma absolute, oh sorry, not this, sorry, e power minus j, and let's say tau is 7, j 14 by f, and here I will plot absolute value of your h2, and this is hold off, and I'll have legend as question 9 channel, then this is question 8 channel, then your y label is frequency response, your x label is frequency. Okay, let's run this. So this is what we are getting, something like this. Now if you observe here, let me just increase line width so that it's visible properly. So line width 2, and similarly I can add line width. This is for h2, this h1. Line width as 2. Okay, so let me run this now. So this is something that I'm getting. Let me put on grid. Okay, so now if you observe here, for question 8 channel it is constant, but for question 9 channel it's varying with frequency. Okay, so what I'll do is, okay, so in order to discuss this, I'll copy paste this into my PDF or in my tab, then we are good to go. Any questions in this coding part? If not, I'll move on to my uh, what do we say, my tab. So this is what we have seen just now. Okay, so this is what we have seen just now. So this particular plot, blue one, was for your question 9 channel, and your this plot here, this orange one, is for your question 10 channel. So what we observe here is this question 9 channel, or this channel which we have here, this varies with frequency. So it is selective, its response is selective to frequencies. So for different frequencies it responds in a different way. So such a channel is known as frequency selective channel. So this is known as frequency, let me write it in better format, frequency selective channel. And this particular line we have discussed already. This particular line is constant with respect to your frequency, which means that frequency this is frequency flat channel. Now considering these two, this frequency selectiveness, we need to modify our communication systems accordingly, which is not a part of this course, but yeah, these two are two different types of channels. Any questions till this part? Okay, if you don't have any questions, then this was all that I wanted to cover today. That's all from my side today. If you have any questions, then please ask. Otherwise, you're free to leave the meeting, and let's discuss your queries on in the summary session. Again, thank you for attending today's session.